Swayam Prabha. Digital India. Educated India.
Immobilized enzymes, and it's hopefully the last lecture on immobilized enzymes. And the thing that we're going to look at today is the effectiveness factor. Okay, the calculation of the effectiveness factor. So the effectiveness factor, what does it signify? It signifies that what is the total amount of reaction that's occurring over the total maximum amount of reaction that could have occurred, right? So that's the idea of immobilized enzymes, effectiveness factor. Sorry. So we did look at effectiveness factors in certain geometries and so on. So if we go to the slide, this is the last thing we did. If you remember, we looked at encapsulated enzymes with reaction taking place both inside and outside, and it was a little complicated in terms of the boundary condition, and we took a simple geometry. And then we ended up with an equation like this: del theta del x square equals phi square being the Thiele modulus, phi square times theta, and the boundary conditions. The boundary conditions included the Biot number, which is the ratio of mass transfer external to internal mass transfer times. And then based on that we got the solution and everything, and we found the effectiveness factor. Now what we're trying to do, what we're going to do in today's lecture is try and obtain a general expression for the effectiveness factor. And I told you while we derived the effectiveness factor for, I think, the normal slab or something, that it comes out to be tan hyperbolic phi over phi, and I told you that this is an expression that you could use for different kinds of geometries provided you make certain changes to phi. That is, you define phi in terms of the effective length L, and so your length L is going to be the length for a slab, half the length for a slab. For a sphere is going to be something else, for a radius is going to be something else, and we'll figure out how to do that today. So that's the first thing we'll do today. So my observed Thiele modulus. So now we come up with the expression for observed Thiele modulus. So if you remember, we had the Thiele modulus, which had the reaction time scale diffusion time scale over reaction time scale, right? So, or in other words, if Thiele modulus is very small, then it means that what does it mean? That diffusion is, if Thiele modulus is much larger than 1, it means reaction is much faster than diffusion, and if Thiele modulus is much smaller than 1, it means reaction is much slower than diffusion, right? So, but the thing is, if you look at it, that Thiele modulus essentially is therefore reaction time over diffusion time, right? So if reaction time is very small, then so Thiele modulus should be diffusion time over reaction time. So phi square equals Td over Tr, okay? So which is A square over dm divided by, what is the reaction time? C naught over R C naught, right? Okay. So this turns out to be R C naught times A square over C naught dm. Fine. So what do you find over here is that if the reaction rate is faster, okay, so Thiele modulus essentially is proportional to the reaction rate. Now this, what is this reaction rate? The question is, what is this reaction rate? When you write a Thiele modulus, you write the reaction rate in terms of C naught, right? What is the C naught? What is the concentration? Yes, that is what is typically taken. So the Thiele modulus essentially is the maximum concentration or the initial concentration or the boundary concentration. Now that obviously is not a true representation of what is going on in the system. Why is that? Because the boundary concentration is much higher and the concentration inside is much lower because of diffusional limitations or mass transfer limitations. So what we want to come up with is a expression for the observed Thiele modulus. So the actual Thiele modulus is RC naught A square over dm C naught, but that's a intrinsic Thiele modulus, but the actual Thiele modulus or the observed Thiele modulus, it should be based on not the reaction rate evaluated at the surface, but what? But the no, the intrinsic reaction rate is the one that's evaluated at the surface. Actual reaction rate, which means that at which point, you know, inside the matrix the reaction rate varies from point to point, right? The actual reaction rate at which point? No, the concentration is maximum at the exit, at the surface. So then there's no point. Then the Thiele modulus is defined as based on the concentration on the surface. Concentration is maximum at the surface. Okay, let me draw this and matrix. You know, I don't know why you're confused. So this is my concentration at the surface. Let's call this C naught. Okay. So my Thiele modulus is defined on so the reaction is defined on the intrinsic reaction rate is defined based on that, and my phi square is defined based on this reaction rate. What I'm trying to say is that this is not the correct representation of the Thiele modulus. If I want to call my observed Thiele modulus as this, then this should be a square C naught over dm is fine, then something else over here, reaction rate evaluated somewhere else. Where? Where is it evaluated? Where should this be evaluated? Because it varies from point to point, right? See, let's understand two things, that the surface reaction rate is not a true representation. Okay, that's the maximum reaction rate possible because the concentration is maximum there, and concentration inside the matrix is varies from point to point and varies from point to point because of mass transfer limitations. Now, which point? This is a very straightforward answer and you should come up with, unless you're really groggy. I mean, you know, at which point should this concentration be measured at? It varies from point to point. Do you agree with that or not? Then which point should we measure it?
It should be area average.
You should average, yes. It's whether a volume average, typically a volume average. So this is what we have, the RC, the average of that. So you take at different points and then take the average of this. It's as simple as that. So how can I write this? So now once I've gotten this, so let's call this RV. Okay, I'm not putting the C in there. Fine. So this I can write now as right. So this is my phi square. What is this? What is RV? Huh? Yeah. Effectiveness factor. Okay. So my observed Thiele modulus is actual Thiele modulus or intrinsic Thiele modulus times the effectiveness factor. Okay. So this is what we have on the screen as well, just the same thing what I showed here. So this is done here. If you see what I did was for a general reaction, and what is shown here is for a first order reaction. Okay. So just RV C naught is represented by kV times C naught, and this is what you have. I think, yeah, I think there is a this kV cancels out. There's a, don't worry about this on the screen. I mean, I think there's a mistake there. This shouldn't be kV actually, because kV is in the denominator anyway. Yeah. So this is correct, that observed reaction rate over interface diffusion rate. So the observed Thiele modulus is the effectiveness factor times the actual reaction, the intrinsic reaction rate, which is the observed reaction rate. So right. So the effectiveness factor times the intrinsic reaction rate is observed reaction rate. So the observed Thiele modulus is observed reaction rate over interface diffusion. Okay. So this expression is correct over here, and there is a problem with kV over here. So, these are not correct. So, this expression is correct if you want to write that, but what we wrote is essentially right before on the paper. Okay. So, now we come to this concept of the generalized expression for eta, which is something that I mentioned to you in the last class or the class before that, is that you can come up with different expressions for eta for each of the geometries, but those are hard to remember. So, what we want is a generalized expression for eta, which you want to remember, and that generalized expression, in that the phi that is there, okay, the Thiele modulus or phi square that is there, is defined in terms of the length scale of the system, and this is known as, what is this phenomenon known as? I used the word last time. Shape normalization, right. So, for different shapes you can come up with the same expression, and as I said before, what did I say, that the expression that we are going to use is not going to be completely accurate for all shapes, but it is going to be very close to accurate. So, there is going to be 5-10% error maybe, but even with 5-10% error you are pretty close. So, because you can, in shape normalization you cannot have 100% accuracy. Okay. So, the expression that we are going to use is this, eta equals tan hyperbolic phi over phi, and does it ring a bell? Yes, it does, because this is what we had obtained in the first calculation, right, when we did the slab, yeah, so transfer, in a mass transfer in reaction in a slab. So, what is the difference that is going to be here? The difference is that phi that we are going to have is going to be defined not necessarily in terms of the length, but in terms of length scales that are related to other geometry. So, what are those? So, phi square is defined as this, say this for a first order reaction, and if it is not a first order reaction, how do you redefine your phi square? This for a first order reaction, then if it is not, then what do you do? I just did it few 5 minutes back. RVLC square over C naught, R at C evaluated at C naught L square divided by C naught D effective, right. So, now this L that you have over here, phi square. So, why I am trying to tell you this, why am I trying to define that, is because it is not that all reactions are first order, right. So, and you should be able to define the Thiele modulus for reactions which are not first order, right. So, for reactions which are not first order, Thiele modulus is defined just the way I wrote on paper a few minutes back, R C naught, R of C naught times L square divided by D effective C naught, right. And this L that is here is half the width for a rectangular geometry. So, if your width is say 2b or something, then your L is b, half the width. It is half the radius for a cylinder and 1/3 the radius for a sphere. Okay. So, this is something that you need to remember. I do not expect you to remember all the formulas, but this is an important formula that you need to remember. Eta is tan hyperbolic phi over phi, phi square is R C naught L square over D effective C naught, or equals kV L square over D effective for first order reaction. L is W over 2 for rectangular geometry, half the width, half the radius for cylinder, and 1/3 the radius for sphere. Okay. So, this is something I want you to remember. Done? Okay. Now, what we will do is we have looked at different cases before, and what I am going to do with the use of this observed general shape normalized formula and the previous formulas is going to look at limiting cases. How do limiting cases help us? Because it helps us calculate the asymptotes of the system. Okay. So, so first case that we are going to look at is where the Biot number is much greater than 1 and phi square is much lesser than 1, or in other words, the system is completely reaction limited. Okay. So, for reaction limited, what do you need? You need phi square is much lesser than 1, or in other words, why the two conditions necessary? Phi square is much lesser than 1 means that the reaction time scale is much greater than the interface diffusion time scale. Now, why do you need two conditions? Why not that? Can you define completely reaction limited systems using phi square greater much smaller than 1? Why do you need the other condition? Why do you need the second condition? And the second condition involves Biot number, right? What is the Biot number? Biot number is T interface over
Between the surface and outside.
yeah TD over TM I think, yeah. So this is much greater than 1, okay, which means that the what does it mean? Now you should be able to tell. Slow, huh? Slower, yeah. Internal mass transfer is much slower, much slower. Right? Now can you make sense of what I am trying to say here? So phi square much smaller than 1 means that TR is much greater than TD, right? And fine, you see what I am saying here? Do you see now? So what do you get? Is that clear? So why do you need this now? Is it making sense? You have 3 time scales, and in order to define a system as completely reaction limited, you have to show that the reaction time scale is the smallest of all 3. It's not enough to show that the phi square that you have over here, for example, is much smaller than 1 means this, okay, and this implies that TD is much greater than TM. So it is not enough to say that the reaction is much slower than diffusion, internal diffusion. You have to also show that reaction is also much slower than external diffusion, okay. So which means that the reaction has to be the rate limiting step. So this is something that you need to understand, that when we had 2 processes in the system, it was enough to show that one of the processes is slower than the other in order to call it a reaction limited or a mass transfer limited. When you have 3 processes in the system, in order to call a system completely limited by one of the processes, you have to show that that process is smallest of all 3, okay. Is it clear? So that is why you need 2 criteria. One is Biot number much greater than 1, another one is phi square much smaller than 1, fine. So once we have done that, so now we can make the approximations. So if eta is tan hyperbolic phi over phi. Now if phi is much small, if phi square is smaller than 1, then phi is even smaller than 1, and phi over so tan hyperbolic phi goes to phi, fine. So then you have eta of 1, okay. So eta of 1, what does it mean? That the concentration eta almost going to close to 1 means as the concentration, since there are no mass transfer limitations, there are hardly any mass transfer limitations, both internal and external, the concentration inside the matrix is more or less close to the surface concentration. Is that what it means, right? So which means that the reaction is more or less taking place at the close to the surface concentration, fine. So then the Thiele modulus, observed Thiele modulus equals the intrinsic Thiele modulus. So because observed Thiele modulus is eta times intrinsic Thiele modulus. So as a result, observed Thiele modulus is same as the intrinsic Thiele modulus, right. So if my observed is so if my intrinsic Thiele modulus is very small, much smaller than 1, then my observed Thiele modulus is also much smaller than 1, because we just showed that they are equal, okay. So now this means that interface diffusion is, because now, so what does phi square much smaller than 1 means? That interface diffusion is much faster than reaction, right. So now if this is the case, and interface reaction is much faster than interface diffusion, sorry, is much faster than reaction, intrinsic reaction. Now if big phi equals small phi square, then it means that interface diffusion is much faster than observed reaction as well. Is it clear? Okay, shouldn't be any confusion, because eta is the ratio of observed reaction to intrinsic reaction. Now eta means eta equals 1 means that observed reaction is equal to intrinsic reaction. Now phi square much lesser than 1 means interface diffusion is much faster than observed intrinsic reaction. It also is also much faster than observed reaction, fine. So, this is one of the limiting cases we did. Are you done with this? So, we will go to the next case. So, so diffusion is not limiting, this is very straightforward. So, the second case that we look at is the other limit, not a complete limit, but to some sort. So, Biot number much greater than 1 and phi square much greater than 1. So, you have to tell me very quickly. So, I already gave you the definitions of both. So, you have to tell me in this case which one is the limiting one, it is already written. So, but you have to show that which one is the limiting, which out of the 3 processes Td, Tm and Tr, which one is the limiting one. So, here Biot number is much greater than 1, which means Td is much greater than Tm, right, and phi square is much less than, sorry, phi square is much greater than 1, phi square is much greater than 1, which means that Td is much greater than Tr, okay. So, which means Td is much greater than Tm and Td is much greater than Tr. Now, I cannot write the kind of inequality I wrote before, because I do not know really relationship here between Tm and Tr, but one thing I know is that Td is the slowest of all, is the smallest. So, it is now limited by internal diffusion. So, it is always like this. So, whenever a relationship is given or some inequalities are given between these two numbers, you have to use these two numbers very quickly to figure out which is the largest time scale, or in other words which is the rate limiting step. Okay. So, if that is the case, now what I find is this pretty straightforward again. So, phi square is much greater than 1, and we presume that if it is much greater than 1, we presume that phi square is greater than 9, say. If phi square is greater than 9, or in other words phi is greater than 3, then tan hyperbolic phi equals 1. Okay. So, tan hyperbolic phi is 1 for all phi larger than 3, right. So, you can go and put that over here, and what you find is eta goes as 1 over phi. Eta is inversely proportional to the square root of the intrinsic Thiele modulus. Phi is, remember, the square root of the intrinsic Thiele modulus. So, how do you obtain the observed Thiele modulus now? You simply multiply this by the intrinsic one by eta. So, observed Thiele modulus is eta times phi square. Now, eta itself is 1 over phi. So, this turns out to be phi, right. Eta itself is 1 over phi. So, this comes out to be phi. Now, what we find from this is that phi square much greater than 1, and this implies that big phi also, that is, if intrinsic Thiele modulus is much greater than 1, then the observed Thiele modulus is also much greater than 1, right, because though it is not as high in terms of the, I mean, it is not as high as phi, because it is not equal to phi square, but it goes as square root of the Thiele modulus. So, if the square Thiele modulus is 100, then the observed Thiele modulus is 10. Okay. Why do you think so? Can you explain physically that last time what we had, that the observed Thiele modulus equals the intrinsic Thiele modulus, but this time we do not have that. We have that it is not equal to, but it goes as the square root of the intrinsic Thiele modulus. So, can you explain that physically? Why does it not go as the directly, is not directly proportional, but it goes as a square root of that? Because of internal diffusion limitations. So, because of internal diffusion limitations, the concentration gradient is not uniform inside, right. Okay. Even if it is smaller than the external one, it is not uniform inside. So, as a result, the observed Thiele modulus is smaller than the intrinsic Thiele modulus, It's large. If the intrinsic Thiele modulus is large, again it is large, but because there are diffusional limitations present in the system, what does it mean? It means that the if phi square is much smaller than larger than 1, it means that reaction is very fast in the system, right. So, reaction is very fast. As a result, the concentration is not going to be very high. Okay, the concentration is not going to be very high inside if the reaction is very fast. But still, what this means is that if there are internal limitations, diffusional limitations present in the system, then there is going to be a concentration profile. It is not going to be uniform. Okay, it is not going to be very high, but even without a small number, you can have a profile. You see what I am saying? So, that is what it is trying to say. It is not a uniform number. There is going to be a profile, but it is going to be a small number because concentration is reaction is very fast. Okay. So, this is what we get, and so what we can do is, if we want to measure experimentally, the last thing you see on the page here where the pointer is. So, if you want to measure experimentally what my observed reaction rate is, because this is something you might want to measure, then this is how you do it. So, observed reaction rate. So, what you do is you put this side, the left hand side, you just substitute the observed Thiele modulus, the right hand side you substitute the square root of the intrinsic Thiele modulus, and based on that, so L cancels out over here, one of the L's. So, you get the observed reaction rate equals square root of kV over d effective, one d effective cancels out here, sorry. So, square root of kV times d effective times kV C naught over L. Okay. So, this is my observed reaction rate, because why do I want to measure? Because see, intrinsic reaction rate is easy to measure. How? Because if you simply measure the rate constant, which is easily available, you can measure the intrinsic reaction rate. Okay. If it is a first order reaction, it is just proportional to that times the C naught. But observed reaction rate is very hard to measure. Why is that? Because you take a pellet or something, or immobilized enzyme, and at each point you have to, inside the matrix, you have to go and measure the concentration, then you have to multiply by the rate constant, and then you have to average it out over the volume, which is a very hard thing to do. So, that is not the best way to measure. So, we are trying to figure out what could be the other ways of measuring the observed reaction rate, and this is one of the ways that we find over here, is that you can measure the intrinsic reaction rate, the effective diffusion coefficient, length of the matrix, and the concentration, and we find a formula to without measuring the observed reaction rate, actually we find a formula to be able to evaluate it. Okay. So, this is what, so we do not measure the observed reaction rate. So, earlier what was we trying to doing? We are trying to solve the whole problem and everything, and obtain the concentration profile, and so experimentally is very hard to measure. So, there are two ways. One is to actually solve for the concentration profile in the system theoretically, and use that to measure my observed reaction rate, right, because observed reaction rate is the integral of the concentration rate constant times the concentration over the domain. So, that is one procedure. The second one is to be able to measure it in terms of other parameters, which is what we are trying to do, but remember that is something you can do only in limiting cases, where one of the three processes, internal diffusion, external mass transfer, internal mass transfer and reaction, one of the three processes is very slow as compared to the other two. Only in those limiting cases can we do it. Okay. So, this is what we get. So, the observed reaction rate is what we said just now, kV times the effective square root of time, that times kV times C naught over L. Okay. Fine. So, let us do the last case. I think this is the one which is the case with finite bad number. Okay. So, we did the case of very large bad numbers, but what happens in the case of finite bad numbers? Formula that we used before was where there was no external mass transfer limitations, right. If you remember, let us go back, this one that we used over here. Okay. Why did we use it? Because there was no external limitations, because all these cases that we considered before, the bad number was much greater than 1, which means there is no external limitations. Now, if there are external limitations, we derived, let us see, yeah, here. So, this is the expression we derived, right. This is, so if you look at this expression, what happens in the limit of bad number going to infinity? Okay, this goes to tan hyperbolic phi over phi. So, this is the expression, general expression. So, in this expression, in the limit of bad number going to infinity or very large, this goes to tan hyperbolic phi over phi, which is what we used over here for the last calculations, because we looked at the two limiting cases. In both limiting cases, bad number was much larger than 1. So, now we look at the intermediate case where bad number is not very large, it is not going to infinity, which means that we have to use the whole expression. It can be tan hyperbolic phi over phi, it has to be tan hyperbolic phi over phi multiplied by this factor over here. Okay. So, 1 over phi tan hyperbolic phi over bad number plus 1. Okay. So, I suggest you write this expression for eta. You have it before also, but just for the sake of remembering, you write this. So, phi square cancels out in the numerator and denominator, one of them. So, you get phi tan hyperbolic phi divided by phi tan hyperbolic phi over bad number plus 1. Okay. Then what we are going to do is we are going to do some special cases on phi. So, bad number is finite over here, but we can take limits on phi. Okay. So, what did we do last time? Last time we assumed bad number to be infinite, and then took two limits of phi much smaller than 1, much greater than 1. Here we will assume byte number to be finite, and then we can take limits on phi. Right. So, the first limit we take again is phi greater than much greater than 1. It does not even have to be much greater than 1, as we showed last time, is just if its phi square is greater than 10 or something, then we can assume this tan hyperbolic phi over phi, and there is a lot of simplification that is possible. So, byte number, so observed Thiele modulus is byte number times phi divided by byte number plus phi. Okay. So, what do you find over here? If you take the observed Thiele modulus, 1 over phi would be 1 over phi is 1 over byte number plus 1 over intrinsic phi. 1 over big phi would be 1 over byte number plus 1 over intrinsic phi. What does this suggest? Physically, what does this suggest? We had done something like this, not exactly the same, but something like this before. Which two resistances?
One would be both mass transfer.
Two mass transfer resistances are in series, but look at this carefully. They are not exactly in series. Okay, it is not the summation of the linear sum. Okay, this is a mass transfer. You can signify this as a mass transfer resistance. Then it becomes, this one looks like the diffusion resistance, but square root of that, because actual diffusion resistance would be given by 1 over phi square. So, it's a summation of the resistances, but not a linear sum of the resistances. One is linear and the other one is goes the square root of it. Okay. So, this is what you need to remember. So, this is for a finite byte number with phi square much greater than, I mean basically 10 would work, actually phi square 10 would work. So, next our aim always is, what we are trying to do is trying to find out what my observed Thiele modulus is, or in other words what my observed reaction rate is based on other quantities, because I do not, I want to be a little, I am a little lazy, so I do not want to be measuring the actual reaction rates. So, what I do is very straightforward, simply in this formula I go and put all my defective in byte number and the intrinsic Thiele modulus expressions for them in terms of the effective diffusion coefficient and the mass transfer coefficient Kf, L, the length, K average, and which is the partition coefficient and everything, and this is the formula that I get, which I can use. Okay. So, this is one limit that we are looking at, and to go a little quick today, because I will finish this little bit. Fine. So, now your RV, that is your reaction rate, observed reaction rate, you can measure in terms of this, and this is the expression that you get. So, if you want, you can write it down. So, this is proportional to the Kf is the mass transfer coefficient, Kv is the partition coefficient, D effective diffusion, and length L. So, we did first we did the byte number much greater than 1, next we did byte number finite, and the last thing we will do in the limiting cases is byte number small. Okay. What happens in the limit that the byte number is very small, or in other words it is limited by the external mass transfer. Okay. So, if byte number is very small, then eta over here, let us go back and look at that formula. Eta that you have over here goes as phi square, I think if this is very small, then this remains. So, I think byte number over phi square, okay, right. So, this goes to the numerator, byte number goes, so if you take byte number, so you will have phi tan hyperbolic phi plus byte number, and 1 goes to the numerator. So, this one you can neglect. So, you will get byte number over phi, just by, I think, no, sorry, this is we are looking at the observed Thiele modulus. So, let us look at the, if you look at only the eta, then you will have byte number over phi square, right, phi square, yeah, byte number over phi square, because, right. So, I will show it, I will show it quick, running out of time, but so eta equals tan hyperbolic phi over Okay. So, in the limit of Biot number going to very small, this is a term you neglect and you end up with Biot number over p square. So, this is the third limit, Biot number much smaller than 1. So, we did first Biot number much greater than 1, then finite, and this is the third limit. Clear? So, let us go quick. So, if that is the case, then big phi, that is observed Thiele modulus, which is eta times phi square, is simply Biot number, okay, which means what? Which means that it is only limited by external mass transfer coefficient. Okay. That observed Thiele modulus is independent of reaction, internal reaction, and it is only dependent on the external mass transfer. Okay. So, the RV that we are trying to find out over here is the effective KAV C naught Biot number over L square. Okay. And what you find over here is, look at this, very interesting, that it depends only on the external mass transfer. Okay. Why? Because Biot number already has a D effective, which will get cancelled with this D effective, and you will only be left with the external mass transfer coefficient. Is it clear? Right. So, because Biot number itself has a D effective in it, so 1 over D effective or something like that, which will get cancelled and L square will get cancelled. So, what it means is that the observed reaction rate, what you observe, is dependent only on the external mass transfer. So, whatever is the rate of external mass transfer is the rate of external is the rate of reaction. So, if you have 3, 4, 5 or n number of processes in series, right, in series, that is the most important thing. If you have n number of processes in series, and if one of these processes is limiting, then the rate of the overall process equals to the rate of the limiting process, right, so something you know. So, this is exactly what we have over here. So, Biot number very small means the external mass transfer is limiting, and because external and internal mass transfer and reaction are parallel, but external mass transfer is in series with these things. So, if external mass transfer is limiting and is the slowest step, then the overall rate of reaction equals to the rate of external mass transfer. Right. These are things that we can derive intuitively, we can come out with intuitively, but these are very concrete ways of showing this. So, in the next few minutes we have, what we will do is, we will show the derivation of the model using Michaelis-Menten kinetics instead of first order. So, what we had been doing till now is that mostly using first order kinetics. Okay. So, as I said, what is our objective? Is objective is to actually predict what happens in a Michaelis-Menten kinetics, because that is what is important in immobilized enzymes, but we have no way of predicting that, the reason being that these are nonlinear equations and we can solve them. So, what we do is we predict the two asymptotes of the zeroth order and the first order. We had not done zeroth order in many cases because it is much easier to solve, and what we find in zeroth order is that we did some cases. What we found was that the effectiveness factor equals 1 for zeroth order. The reason being that there is plenty, zeroth order itself means that there is plenty of substrate inside. So, we looked more at the first order and also with some cases of the zeroth order, and we know that the actual case is kind of bounded by these two. So, what we do is there is one single case which we can actually solve analytically using Michaelis-Menten kinetics. So, just as one example, the last example of this chapter, we will solve this case using Michaelis-Menten kinetics, and this is a case where you have the external you have the surface reaction taking place. Okay. So, this is that old example, if you remember, that we had with, we have the enzyme over here, we have the matrix over here, and the enzyme is immobilized on it using receptors which are covalently attached to the surface, and the substrate is coming in and reacting over here. So, this is the only case where we can use Michaelis-Menten kinetics and still get an analytical solution. If you remember, there were two approaches to this. What were those two approaches? We did this, there are two approaches we had taken to this. One is the boundary layer approach using the diffusion reaction equation, and the other one was the mass transfer coefficient approach. Okay. We did it like 3 or 4 classes back, 3 classes back, I think. So, the diffusion reaction equation or boundary layer convection diffusion reaction equation using boundary layer theory is not something you can solve analytically for a nonlinear reaction. It is not even something that you can solve analytically for a linear reaction, let alone a nonlinear one. So, obviously, that is ruled out if you want to get an analytical solution. So, the one that we are left with is mass transfer coefficient, the use of mass transfer coefficient. So, let us do that. So, this is, if you remember, that this was our this was our boundary condition. Lisa, just tell me if you have any problem with this, that this was a boundary condition, that at at y equals 0 at this point, the flux that when y at y equals 0 was Kf, that is mass transfer coefficient, times C naught minus C naught is the boundary, is outside the boundary layer, the concentration outside the boundary layer. CSO is given in the picture, here I just refer to it as C naught, but same thing. So, C naught minus the concentration at y equals 0 at the surface, right. So, that is the amount of material that is coming in. Now, what was the reaction previously? Previously the reaction we looked at the first order reaction, okay, so which means that it was some Kv times C or K times C, Ks times C. Now, we are looking at Michaelis-Menten kinetics, which is nonlinear. So, before we actually go and solve this, try and solve this, what we do is make the system dimensionless, and it is important. This is really important in this case, it is not out of fancy that we do it. So, how do we make it dimensionless? You have to be slightly careful here. So, theta is a new dimensionless concentration, which is the concentration at the surface divided by the concentration outside the boundary layer. Okay. So, Cy at C at y equals 0 divided by C outside the boundary layer C naught. Beta is a new dimension, a new variable that you define, which is C naught over Km. Okay. This is again dimensionless variable C naught over Km, and Damkohler number over here, and you have to be careful with this, is defined as R max. The double prime here signifies this is a surface reaction. Typically, it is nothing to do with derivatives. Okay. Typically, Rs is used, or R double prime is used for surface reactions, and Rv or R triple prime is used for volumetric reactions. So, again nothing to do with derivatives over here. So, Damkohler number over here is given as R max double prime over Km times Kf, okay, Km being the Michaelis constant, and Kf being the mass transfer coefficient over here. So, this is something new, and we have not defined Damkohler number in this way previously. Why? Because we did not have a nonlinear reaction, we never handled a nonlinear reaction before. So, this is the first time we handle a nonlinear reaction, and so we come up with these sets of variables, okay. And you will see that how these variables, why you might want to ask me that how do you come up with these variables at this point of time. Theta is very straightforward, but these two variables are not as straightforward, the dimensionless variables, and why do I come up with that? Once I recast the equation in dimensionless form, you will start to see that why I do that. So, now see this. So, what have I done? I have Kf. So, this only this part of the equation that is there, okay, this part over here. So, this is the one that I make dimensionless. So, Kf C naught minus C equals R max C over Km plus C. Okay. So, Kf if you take to this side in the on the right hand side, then you get R max over Kf, right, and remember R max over Kf is this side here. So, this side gives you 1. So, divide the equation both sides of the equation by C naught. So, this will give you 1 minus theta, right. So, this will R max. So, divide both sides again by Kf Km, okay. So, you will get Damkohler number over here on the denominator times theta. This Km goes from the denominator because you have divided that, plus beta times theta. So, beta is because beta comes because of C naught, okay, and C naught and Km because you have divided both sides by Km, and theta comes because of C over C naught. So, C over C naught, is that fine, or you do not want me to go through that step? Fine, right? Okay. So, now it is pretty straightforward for me. What I am going to do, this is a quadratic equation, and I am going to solve it directly. So, why don't you put the equation that form and quickly get the solution. So, this is the quadratic form that we have, 1 minus theta plus 1 minus beta theta equals Damkohler numbers times theta. And then you will get, once you open the brackets, you will get 1 minus theta plus beta theta minus beta theta square equals dA theta. As you collect the coefficients, so then you will get the final form of the quadratic is beta theta square plus dA minus beta plus 1 times theta minus 1. Right. So, then once you solve this, this is your value, this is your expression for theta, beta minus dA minus 1 plus dA minus beta plus 1 square plus 4 beta, the square root of that over 2 beta The reason you neglect the other route is because it is not feasible, it is not in the physical regime, right. So, then what you are supposed to do is find the rate, the eta, the effectiveness factor again. So, the eta is here, if you remember the way we defined it before, is that eta at the surface concentration divided by eta had it been at the concentration outside the boundary layer, right. So, eta at C s or C at y equals 0, sorry, rate at C s or C at y equals 0 divided by rate at C equals C naught, fine. So, slightly different from before because of the nonlinear nature, you get C at y equals 0 divided by Km plus C at y equals 0 times Km plus C naught over C naught, right. So, no problem. So, now we can express this in terms of beta, remember, right, because beta was defined as Km over C naught, if you remember, C naught, yeah, C naught by Km, yeah, C naught by Km. So, this is what we do, you can divide the whole thing by C naught by Km. So, theta times 1 plus beta over 1 plus beta theta, right. So, now once we substitute this, you can get your expression for eta, okay. So, you already got your theta, you can substitute that back over there and you can get your expression for eta. So, which is again a pretty nonlinear expression because that is what is expected. Fine. So, the last thing we will do today is, have you written this down? Okay. So, the last thing we will do today is to try and plot this. Okay. Okay. So, before that I think we have to do some quick limiting cases. So, the limiting cases are things that you know, that beta going to 0 it is a first order reaction, beta going to what value, it is a 0th order reaction? No, not 1, what? Infinity, right. So, beta going to infinity is the 0th order reaction. So, so if you look over here, so beta going to 0 and you can check over here. So, for example, here this was an expression. So, beta going to 0 is the first order reaction, beta going to infinity you had a 0th order reaction, not beta equals 0, right. Beta equals 0 is the first order, beta going to infinity is 0th order. So, theta, if you put that in the quadratic form, and this is something that you just again we do not have a lot of time, but this is something this is not very straightforward. If you want theta going to 1 over dA, this is not very straightforward. Okay, this I think you can get from the quadratic form, but there is another one that it is not so easy. Let me go through this and then, because we do not really have a lot of time. So, let us go through this quick and then if there is a problem with the calculations I will come back to it. So, theta for this case beta going to 0, that is first order, it goes to 1 over dA, 1 over 1 plus dA, okay, and the eta therefore comes out to be 1 over 1 plus dA, okay. So, here for example, if you go and put that, so beta equals 0 you have put in. So, this is simply equals to theta, right, eta is simply equals to theta. So, your theta goes to 1 over dA. How do you 1 over 1 plus dA? You can put it in the quadratic form and get this, and eta will be 1 over 1 plus 1 over 1 plus dA again, because it is equal to theta, okay. The other case is the beta going to infinity, the 0th order reaction. Now, this is there is a little problem in getting this solution. For example, this is a quadratic form, right. Now, with beta going to 0, for example, this is your solution that you get. With beta going to 0, you can see what is the problem with beta going to 0. You cannot put this, that is what I said, the slight problem over here. So, you cannot put this directly into this form, right, because beta is in the denominator. So, what you need to do is you put your beta equals 0 in the quadratic form itself, fine, and then you get theta straight away equals 1 over 1 plus dA, clear. So, this is just a quick little trick, okay. Is it clear, Lisa? So, you cannot put it directly into the quadratic form because this will blow up if you do. So, just put it in, no, you cannot put it in the solution, put it in the quadratic form and get it. Similarly, the beta going to infinity, also you have to put it into the quadratic form and get this, and what you will get is eta going to 1. Okay, beta going to infinity, eta going to 1, and this is something that, why am I doing these two limiting cases? Because these are two limiting cases I have already solved before, if you remember that eta going to 0, eta goes to 1 over 1 plus dA for beta goes to 0, that is the first order case I did separately, and then I did the 0th order case where I told you that eta goes to 1. The reason eta goes to 1 is because there is no effect of boundary layer essentially, and the concentration at the surface equals the concentration at the boundary layer. Okay, so what I am doing is this: whenever you do a nonlinear problem, this is usual thing that you do always, that whenever you do a nonlinear problem, it is important to check the two asymptotic limits of the nonlinear problem with the two solutions that you know. So that is what we are doing. We are just checking with the two solutions that you know to make sure that it works, A, and B is to figure out that it stays within the limit. So the last thing I will show you is the plot of eta versus beta. Okay. So this is the plot for the first order reaction. Okay. This is the plot for the first order reaction, beta going to 0, and this is eta equals 1. I should have written that, but I haven't, so please make a note over there. So this is the line of eta equals 1, the line parallel to the x axis. Okay. So for eta going to infinity, what did you have? You have this line extending all over. Okay. So what happens is that as beta starts to increase, or in other words, the system tends away from first order towards 0th order. So Michaelis-Menten kinetics means it is somewhere within the 0th and the first order, right, a fractional order. So this is the first order, and as soon as beta is a number greater than 0, a positive number, it means that the order is fractional. So as it tends to become fractional, the eta, the effectiveness factor, increases. So which means that Michaelis-Menten kinetics essentially improves the effectiveness of the immobilized enzyme. So this is a very important thoughts that we want to take away from this whole chapter, because the reason that we are trying to do is that we had shown you first order, we had shown you 0th order, but what is the effect of Michaelis-Menten kinetics? So the conclusion that we have, and this is essentially the conclusion of this chapter also, that the effect of Michaelis-Menten kinetics is to reduce the significance of fluid phase mass transfer effects until surface concentration declines below Km. Okay. So if what do you mean by until surface concentration declines below Km? What it means is that if reaction is very fast and it is being depleted very fast, then at some point of time the substrate is going to be taken away and the surface concentration is going to decline below the value that is given. So if it's, unless that really happens, unless in the Michaelis-Menten constant kinetics the surface concentration decreases to that kind of value, it always improves. So if you look at this graph, this is a first order reaction, the Michaelis-Menten is always going to improve, which means that it reduces so the kinetics itself is such that the effect of mass transfer is reduced because of that. So the mass transfer effect that you have in a first order reaction is more than the mass transfer effect that you would have in a Michaelis-Menten. So come to think of it, it's not very it's something that's quite intuitive. The reason it's quite intuitive is that think of this, the mass transfer effect or mass transfer limitation that a system would have on a 0th order reaction is much less than a first order reaction, right. So when the order goes fractional, it hurts less. Again, you think of this in this way, the mass transfer effect that a system will have on a second order reaction is more than a first order reaction, right. So higher is the order of the system, then higher is the effect that mass transfer limitation has on the system, right. So lower is the order of the system, lower is the effect of the mass transfer limitation has, and come to think of it, Michaelis-Menten is a complicated kinetics, but the effective order is a fractional order, right. So because it's fractional order, the mass transfer has less effect than that it would have in a first order. So this is one of the important. So we do 0th order, we do first order all through the chapter, but this is one of the important things that we take home. So is there any quick question on what we did? So just to summarize, we did surface reaction, we started with reaction outside, we took a sphere on which the matrix, a spherical matrix on which the enzymes were immobilized on the surface, and we looked at outside concentration variation. Then we took a system where the matrix was immobilized inside. We took a system where the matrix was immobilized on a flat plate on the surface. We took a system where all these two things were coupled. It was on the surface, it was inside. Then we looked at different geometries. We looked at the effect of 0th order, first order, and finally the effect of Michaelis-Menten. So this is in a nutshell what we did in the last 4 or 5 lectures in this chapter. So tomorrow we'll start a new chapter on microbial growth. And so if there are any quick questions, I'll take it right away. Okay, then we'll stop this, and so we'll continue tomorrow with the new chapter. So thank you.